All righty. Welcome, folks. Thank you for attending this session. My name is Sayak. I work as a deep learning associate at 5 Search. I work at the intersection of computer vision and deep learning. And today I'd like to talk to you about model optimization, specifically in the context of deep learning. And here's a little bit more about myself. So as I primarily work with TensorFlow and Keras, I like to mention that I call model.fit at 5 Search. Recreationally, I contribute to TensorFlow Hub, and I'm a huge Netflix fan. And all of my coordinates are at sayak.dev. That's sayak.dev. And I acknowledge the entire presentation deck to a bunch of machine learning GDs and Khan from Google for providing their valuable feedback. And the ideal audience for this session would be the machine learning engineers that are looking for ways to optimize their models for deployment purposes. So yeah, I do assume that you are already familiar with the fundamentals of machine learning and deep learning, and you are familiar with TensorFlow and Keras to some extent, because all the code examples that we'll be discussing throughout the session would be primarily in TensorFlow and Keras. With that said, the concepts that we'll be focusing on today throughout the session are kind of framework agnostic, and they equally apply to other domains such as uh, natural language pricing, audio, and so on. So here's the brief agenda of the session. We'll be starting off by introducing what model optimization is and why should we actually care about it. Then we'll discuss different areas for a model to optimize to sort of build the leeway for the further discussion uh, on optimization techniques such as quantization pruning. There are other optimization techniques as well, specifically when it comes to deep learning models and stuff. But for the sake of time, in the interest of time, we'll be mainly discussing about quantization and pruning. I'll be also providing you with some practical world considerations so that you can take the most out of this session and apply these things in your own projects. And if time permits, we'll be having a very short question and answering session. That said, you can always, feel free to reach out to me and ask your questions on this presentation and anything in deep learning in general. So throughout the session, I'm going to be using a number of different conventions. So TF would mean TensorFlow, TF MOT or MOT would mean TensorFlow Model Optimization Toolkit, and TF Lite would essentially mean TensorFlow Lite. So let's start. What is model optimization? So model optimization can actually be an umbrella term for reducing model size, speeding up inference time, or reducing the power usage to run a model, but without having to occur the expense of your model performance at the same time. So all of this points come with this hidden constraint of not compromising your model's performance, because after your model is kind of optimized, you would want your model performance to be at par with the original model performance, right? And why should we essentially care about it? And I might just rush uh, at some point because in the interest of time, right? And why should we actually care about model optimization? Because your world class but heavy machine learning models are likely not suitable for deployment. So think of deploying your GPT-3 or BERT based model, which is probably 500 MBs or GBs in size. Think of deploying them to a mobile application, and you cannot at any cost use any cloud based API. So you wouldn't want your application to be of say size 2.4 MBs just for a deep learning model, right? And consider deploying models to tiny devices such as Raspberry Pi mobile phone. The point that I just reflected on. And moreover, heavier models tend to have latency, and latency during serving is not at all desirable. And latency is not at all desirable for mission critical applications. Think of situations where you would want to have instantaneous predictions rather than having batch based predictions. And heavier models can affect the infrastructure cost significantly, which is to say deploying deploying a 100 GB model is probably way costlier than deploying an 100 MB model. I hope you got the idea. And what if cloud-based model hosting is not an option? Think of cost, think of network connectivities, think of privacy and regulatory concerns and so on. So I hope I was able to convince you that model optimization is not just a fancy term. Model optimization is highly related to real world application deployment scenarios. If your applications are supercharged and super powered by deep learning these days. So let us now consider some of the areas for a model that can get optimized. So think about the numerical precision. A deep learning model's parameters and the activations are generally represented in float 32. And I'm mentioning the term generally here because these days we like to train our models using techniques like mixed precision training. But in most of the cases, typically your model's parameters and activations are represented in float 32. So what if we could reduce that numerical precision to float 16 or int 8 and so on? We'll come to that, but just to motivate this point a little bit. So are all the operations in your model's graph needed during the inference? Operations like dropout, many layers that can be that can prove to be redundant during the inference time. And one such operation would be dropout. So although libraries do take care of the dropout operation in their own particular manner, but dropout is typically not an inference time technique, right? So there can be other such operations in your model's computation graph that might not be needed in the first place during the prediction time. And are all the parameters of a model contributing to its performance? Can some of those parameters be pruned, quote and unquote? And pruning is a technique that we'll be discussing shortly in the session. And oftentimes in order to execute a model efficiently, we may need to do some back and forth between GPU and non-GPU based kernels. And doing this thing in an abundant manner can introduce a lot of latency. And this point is explained in the link that I've just included in the deck. And no worries, I'll be sharing my deck with all of you so that you can refer to it if it's needed. And if we were to map these areas for improvement to concrete terminologies, here's how it's gonna look like. So if we were to deal with reduced numerical precision, we should care about quantization. And if we need to cut out some of the operations from our model computations graph, probably techniques like layer fusion, constant folding would be the most appropriate. And if we were to pursue this question that if all our parameters of a particular model contribute to its performance, pruning would be the technique that we should be looking for. And in this session, again, just to reiterate, quantization and pruning would be discussed. So yeah, and quantization in a nutshell. In the interest of time, I'm not going to dig deep into the mathematics of quantization. I'll leave that for you folks in case you are interested and in case you are feeling excited. But in the interest of time, I'll just introduce it briefly. So quantization works by reducing the precision of the numbers that are used to sort of represent your model's activations and sometimes model's parameters and sometimes activations too, because most of the available post-training quantization APIs often only take care of the parameters and not the activations until and unless it's explicitly specified to do so. And that parameter, as we discussed earlier, it's mostly that precision is mostly in float 32. And if we sort of reduce that precision, if we reduce the continuous range of your parameter values to discrete ranges that we can see at the right, then it results in smaller model sizes and faster computations eventually. So that's briefly the idea. And there are two types of quantization mostly. One is post-training quantization, which sort of happens during training, and quantization-aware training, as the name suggests, it happens during training. And we'll get to that shortly. So let's start with post-training quantization. It happens after your model is trained. And here's some code to sort of, motivate the examples further. So here's our humble dataset, the classic Lawrence-Moroney dataset, y equals to 2x minus 1. And here's our humble model that can fit this data. And here's exactly how you would fit it. And here are 3 lines of code that are needed in order to further, quantize this model. So in the first line of the highlighted code block, I am, loading my Keras model into TF Lite converter, in a TF Lite converter object. Then I'm specifying the optimization that that I'd like to choose, and then I'm converting the convert. Then I'm calling the convert method in order to just quantize it right off the bat. And there are different optimization options available, which you can choose according to your needs. But if you choose tf.lite.optimize.default, it sort of works right off the bat. It almost works in the expected ways. So yeah, but which is to say you have got options in case you are not satisfied with the default scheme. And serializing this TensorFlow Lite model is just a matter of 3 lines of code. And there are different post-training quantization schemes available with TensorFlow Lite. Like the one that we just saw is referred to as dynamic range quantization, but there are other quantization schemes, post-training quantization schemes, such as full integer quantization, float 16 quantization, and so on. And based on your application needs, you can mix and match between them and eventually decide on only one scheme. So I have also included a notebook demo that sort of walks you through the entire elaborative process. So feel free to check that out in your spare time. And let us now discuss the quantization-aware training scheme. So it's a no-brainer that quantization introduces information loss that can lead to drop in model's original accuracy sometimes. Remember in the beginning we mentioned that most of the optimization recipes come with this hidden constant of not compromising with your original model performance. So post-training quantization can actually lead to drop in accuracy sometimes, which is exactly why quantization-aware training might be very useful. So what if we could somehow inform the model about this, precision loss during its training? So I would prepare my model for the worst. I will train it in such a way such that it knows how to handle that precision loss in a systematic manner, and enter quantization-aware training for that. So again, let's take a very simplistic code example in order to further clarify this. So here's exactly how you would define a sequential model in Keras. I have intentionally skipped the model definition part, and this is just 1 line of code that sort of instructs your Keras model to get trained using the quantization-aware scheme. And from now on, I'm going to be referring to quantization-aware training as QAT. And this is, and the rest of the things remain exactly the same. You would compile and fit your model in the same way you would compile and fit a regular Keras model. So again, a notebook demo is available for you, so feel free to check it out in your spare time. And the benefits that you get with quantization-aware training are extremely evident, as I would say, as we can see in fact in the table. So the first row represents a regular Keras model that I trained using the flowers dataset. I rather used transferred learning, and the original model size here is 11 MB. I did not, of course, do any optimization and stuff. The validation accuracy is 88%, which is fair. And when I train the same model using QAT, I get the same 100 MB model, but this time I get a whopping boost in validation accuracy of approximately 4%, of more than 4%, in fact. So I get a validation accuracy of 92.91, right? And I sort of took the mean across 5 different training runs. So yeah, you can trust this statistics. And here are the statistics from the quantized model. So the model that was not trained using QAT, the validation accuracy drops to 75.09% in its case. And the model that was trained using QAT, if we quantize it, the quantized model is able to retain the original model performance to a great extent, right? It's still in that 92 zone. So I hope it's convincible enough for you to try the post-training quantization APIs and quantization-aware training APIs that we just discussed. So the recipe so far has been, the optimized recipe so far has been train a model using QAT, uh, probably hybrid quantized model or dynamic, range quantize the model and then evaluate and simply enjoy. Because if you are not enjoying the process, what the hell are you doing, right? So yeah, and you can also train parts of a model. Let's say you don't want to, train the entire model using quantization-aware training because it's very costly sometimes. Rather, you would want to train some layers in your model using the quantization-aware training scheme, and it's absolutely possible. But quantization-aware training scheme has got some disadvantages. For example, QAT can take substantially more time. The green, bar denotes a regular keras model training. And when you incorporate QAT into the scene, the model training time gets doubled up. So this is something you need to take care of. I mean, you need to consider and keep in mind. And full integer enforcement might not be yet possible for QAT, and full integer enforcement is typically a criteria for accelerators like Coral and so on. But it's still a work in progress, and you can check out this issue thread to get yourself updated with the latest developments around this area of enforcing full integer quantization constraints on a QAT model. And QAT also requires your model to be written entirely in keras, and it assumes that you have access to your model, training code and training dataset, which may not be the case all the time. And if QAT fails to produce good performance after the post-training quantization, report it at that point in time, because the entire point of using QAT is to match the original model performance. And if it's not the case, report that phenomenon. And here are some best practices of using quantization in TensorFlow Lite and the model optimization toolkit. So feel free to check it out if you want to dig really deep. And then let's hit this topic, the topic of pruning, which is pursuing this question: do all the parameters of a model contribute equally to the performance? And generally, as it turns out, low magnitude parameters usually do not contribute to your model's performance, and they can easily be discarded. Excuse me, let me have my water. And these parameters can easily be discarded, the low magnitude ones typically. And zeroing out those parameters essentially is referring to as pruning. So how can you discard a model parameter? You simply zero them out and you do not update them during the training process. So, and the process of pruning can take place during training and after training as well. So switching gears to models parameters. So this is like the fully connected model, a shallow fully connected model. And after getting pruned, it may look like this. And again, let's take some code. We are probably starting by defining a sequential model in keras. We are then compiling it and fitting it. And then I am pruning all the low magnitude parameters from my model. And then in order to retain the original model performance, I'm again compiling it and fitting it. So get onboarded with pruning, and I've also provided an extremely well worked out notebook example. So feel free to check it out. So the main advantage that we get out of pruning is sparsity. So sparse neural networks have an advantage of reduced model size when they are sort of compressed. So after you have a sparse neural network, if you sort of compress it using any popular scheme like gzip, then it would result in reduced size. So that's one of the advantages. So you might be wondering at this point in time that this whole pruning thing, isn't this similar to dropout, right? So I'll let I'll allow 20 seconds of time for you to reflect on this question. This pruning thing, isn't this dropout? I hope you had your brainstorming, but it is not actually dropout. So dropout is only a training time technique. It's not, used. during inference, while pruning is used during inference. That's the whole point. There are other differences as well, but this is one of the major differences. So something to think about is a pruned version of a heavy network is yielding almost the same performance. So it's safe enough to say that our initial network is indeed over parameterized with respect to our given data. So we have been over parameterizing our network the entire time, right? Which is sort of a cheating. I won't say it's cheating, but over parameterization is something that we should take into account while, putting our models into production, because it can make your model overly confident on a given set of data. And if you are interested enough, then definitely check out the work on lottery ticket hypothesis by Jonathan Frankel. And there are some best practices in pruning, and definitely check this official guide by the TensorFlow Model Optimization Toolkit folks. This is an amazing one if you are willing to dig deeper into, optimizing your model in the best possible ways in the pruning APIs. Okay. And here's another recipe. So load a pre-trained model, prune it with respect to a given sparsity. So the pruning API is offered by TensorFlow Model Optimization Toolkit, allows you to chase a particular sparsity. So yeah, you have the option to prune your network with respect to a given sparsity, but there can be some performance trade-offs. And then retrain the prune model, quantize the model, and then evaluate. If you are having the expected performance, enjoy, or go back to the same process of pruning your pre-trained network with respect to a given sparsity. And one can train models using pruning callbacks, basically by specifying a pruning schedule. And it's also possible to prune certain parts of your model instead of pruning the entire model. So essentially, we like to retrain the prune model to recover any lost accuracy. And in the coming days, the inference will be faster for prune models if you are using TensorFlow Lite. And make your own optimization recipes and experiment, because again, at the end of the day, deep learning is highly experimental branch of science. So yeah, do experiment and be creative with the process. And here's some resources that that you could use if you are really interested in order to study the field of model optimization further. And if you have any questions around TensorFlow Lite, just shoot an email to tflite@tensorflow.org. And here are some further things for you to explore in case you are interested. And definitely check out knowledge distillation, because it sort of deals with the dark knowledge inside neural networks. And the deck is available here. I would really appreciate if organizers could pop it up on the screen. It's bit.ly/mo-101. And I'll anyway, tweet the link out. I'm on Twitter. I'd love to get connected with you folks. And the organizers are running a short feedback form consisting of, 3 simple questions from this entire session. If you answer, correctly, probably you would get a cool swag bag from organizers. So definitely take the survey and get yourself a chance to win amazing swag. So that's it from my end, and I'm happy to take questions given that we have 6 minutes of time. Okay, so if there are no comments, then I can probably hop off. Okay.